it's like a group. We're like the Beatles. Got to be like the Beatles.
Or
Blackpink. One or the other. Make your choice.
Okay.
So it's like,
either the Beatles
on
or Blackpink.
3.
Walkabout.
I got my shirt.
You got your shirt.
Fired up.
Do you want me to put my shirt
You got a
on?
NASA shirt on? It's just regular
She's
clothes.
just a slob
Regular clothes.
over there. Welcome to Walkabout the Galaxy, the catch-all astronomy podcast where the science is universal, the opinions are personal, and the hosts are hot.
Ouch.
We are strange.
Is it because it's Florida?
You can draw your own conclusions.
All right.
We are strange top, and we're not Blackpink hot.
Oh.
Well,
Yeah.
no.
But who is?
Yeah, exactly.
We are strange top and down the astroquarks, also known as Josh Caldwell.
Jim Cooney.
And Audrey Martin.
Well done, folks. Coming to you from the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including Facebook, Instagram, YouTube, and Threads, period.
Mm-hmm.
I was looking at crazy website names,
Yeah.
and I decided it was just kind of a dark, scary spiral that I didn't
Was it
really want to
really?
go down any further. Yeah.
Yeah.
So that's the end? That's the end of that?
Well, there's
For now?
not on episode 333, which is what this episode is. There are 3 of us here for episode 333.
That's so amazing.
Right?
Oh, when I was younger,
You dreamed about being on episode 333 of a podcast?
Yeah. No, I loved 3, and a friend and me, we made up a holiday on March 3rd, and we just
3-3?
Yeah,
Yeah.
and we would make pastries.
Okay, well, there you go.
Yeah,
This
this is
episode
great.
was meant
for
to
you.
be... I was going to... Yeah, so there was one, for example, called whorepresents.com, which you can, if you spell that out, you can imagine different ways of pronouncing it. You can contact us anytime at wtg@ucf.edu with questions, compliments, and to find out how to get a cool Walkabout t-shirt. Our stumper today is actually just sort of serious.
Good.
Sorry
Deadly
about
serious.
that.
All right.
Good.
It's
That's what we do best.
astronomical. And Charm Quark, who is unable to join us today because it wouldn't have been cool to have 4 people on 333,
So lame.
has texted in her answer to the stumper.
Oh, she did?
Without explanation
But I don't... Yeah.
or elaboration.
Yeah.
So we will mock her for her answer.
Oh, good. Good. Okay, good.
Our stumper today is astronomical. Suppose you were given sufficient time on the James Webb Space Telescope to make a meaningful observation of one target in the sky. So what I mean there is, if you need a month of integration time, you got it. And if it's a bright object or whatever, you just need an hour or whatever.
But
It's
it has
fine.
to be one.
One target.
Got
you get
it.
to point.
Got it.
You
Got
get
it.
one pointing, okay? Mm-hmm. What are you going to look at with JWST?
I would look at the asteroid that's named after me.
Oh.
Because it is too small for that to be like a
Interesting.
real, I could.
Nobody else is going to look at it.
No one else is going to look at it. There's really not a good reason to, aside from I want to see it, and that's kind of it.
Yeah.
And we'd have to look at it for a very long time because it's very small. It's only 8 kilometers.
That's a pretty good size.
It's a pretty good size, but without
pretty good size
without
asteroid.
good justification, no one's going to give me time for that.
I
So
don't know
this is
how-
the only way I would be able to view my asteroid with JWST.
Cool. I wonder, we should figure out how many pixels it would be.
Oh, yeah.
I don't know. It's in the main belt, I assume. It's a main belt asteroid.
It's a main belt. I mean, I could go
Could
through
figure
all
it
of the
out.
steps and pretend like I'm proposing to observe it, and then just not submit it because I wouldn't have a science justification for it.
But we don't need to do that. We can just do some simple geometry to figure out from 1 AU to 2.5 AU or something like that. If we knew what the resolution
true.
of the telescope is, we could figure out
Yeah, that is true.
whether or not it would be more than a pixel. I'm not
I don't think
sure
it
it would be more
would.
than a pixel. I don't know how big my asteroid is, but it's probably 9 kilometers.
Yeah, something like that, probably.
9 or 10, probably. More than 8, probably. Jim, what about you?
Yeah, it's a tough one for me because in cosmology, you don't really look at individual objects. You look at like statistical
Right. You look at the survey type
distribution.
stuff.
Yeah. So I'll just go entirely the opposite direction. I'll look at TRAPPIST-1.
Which one is that?
That's the one with like 7 planets. Multiple ones
Okay.
are in the habitable zone. It just seems like a thing that could use a month of integration time, and you could probably learn something about the atmospheres or potential atmospheres of some of these things. I don't know. I don't know enough about the science of these things to know, but it seems like infrared would be a good wavelength regime to look at those things in, and you might be able to learn something more and see the aliens.
That's right. Okay, that's good. Addie said she'd look at the moon.
Come on.
Lame.
Come on.
Right.
Would she really? She wouldn't really, would she?
For a tenth of a second or something or less.
Like,
or
we're
whatever.
going to the moon. You don't
Yeah,
need to
we
look at it with a
so
telescope.
much data, and I don't know. Okay, this is obviously like, if the all the parameters were correct and blah 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 and whatever, but like the moon is way too bright.
Silly.
Right.
It's silly.
So
It's just,
like,
I know
the
this
data
woman
would
likes
be
the moon,
crap.
but come on.
Yeah.
Also, your asteroid is 2 kilometers.
Oh,
That
somebody's is bigger than the other person.
Some serious
Ooh.
BS.
It is what it is.
What's your number of your asteroid?
What does that tell you? The order in which it was found or something?
28,798.
I'm returning my asteroid. Mine's 29602 or something, right?
Oh, Addie's is 2 kilometers as well.
What's my numbers? 29 something?
I think that means Audrey's just better than you guys.
29,605.
29605. So she has a lower number and a bigger asteroid.
Bigger asteroid.
I'm a better person, so it makes a lot of sense.
That does make a lot of sense to me.
Oh.
Yeah. Yeah.
Are you a better person?
Well, yes.
Apparently.
Apparently I am.
Apparently. You probably wouldn't be as bitter as I am if the situation was reversed. So that probably also makes you a better person.
I might be better.
Yeah. You might be bitter? Is that what you said? Oh. Yeah.
What would you look at?
What would I look at?
Yeah.
I would look at a circumstellar disk. I don't know which one, but one of those cool ones. Let's say Fomalhaut.
Fomalhaut?
Yeah, Fomalhaut.
Fomalhaut.
Nearby star with a disk around it. Maybe some planets forming, something like that.
Oh, nice.
That'd be cool. Yeah. But I'm returning my asteroid and quitting astronomy since your asteroid is
Can I have it? Can I have it? Because I don't have an asteroid.
bigger than
Can
mine.
I have it?
Better than mine. Man.
I'll take a 2-kilometer asteroid any day.
It's like, see if I ever write another major paper about asteroids again.
The community will be very sad.
No, they won't, obviously. Today we'll talk about more challenges to standard cosmology and a plethora of space news, a cornucopia of space news, a veritable trick-and-treaters treat bag of space news, a real Santa's sleigh of space news.
Santa?
Yes.
I love Santa.
It's too early. It's only September.
But
Love
first, this episode of Walkabout the Galaxy is brought to you by Chthonian planets.
What?
Excuse you?
Bless you. If you've ever wondered what it would be like to take a stroll on the surface of a gas giant like Jupiter, but the crushing weight of 300 Earth masses of atmosphere has put you off, take a trip to a Chthonian planet on your next Walkabout the Galaxy. Stripped of those pesky atmospheres by the intense heat and radiation from their stars, these former gas giants leave their rocky and metallic cores exposed for the intrepid exoplanetary explorer. Visitors to Chthonian planet surfaces should be prepared for lava oceans and a rock vapor atmosphere. Chthonian planets experience the warmth.
Rock vapor?
Yeah.
That's awesome.
Yeah.
That's pretty cool. I'm in. That's cool.
So these are hypothesized. We don't know for sure. We haven't unequivocally observed one. There's one or two exoplanets that a couple of people said this might be a Chthonian planet.
Spell that? What?
CHTHONIAN.
Whoa.
Yeah. So you pull that out on some word game. Put that in your back pocket. Chthonian. You can also use, my dad pronounced it tonic, but CHTHONIC. From that same Greek root,
I guess,
meaning earth.
Oh.
Yeah.
What's the tagline?
Experience the warmth. Thank you for keeping us on track here.
You're welcome.
You are a better person than I am.
I'm so happy you finally noticed. North Face?
North Face, is that what you said?
Yeah, like
That's not bad.
jackets or
That's props for
Eddie Bauer.
It's a good thought.
The Bahamas.
You are closer. Micronesia.
Micronesia.
Okay.
Yeah.
There was someone from my undergrad
I was not expecting
who
that reaction.
did went to the Peace Corps, I think, and went to Micronesia.
Okay. Was it
place.
warm?
I haven't talked to her since.
Probably not as warm as a Chthonian planet.
Probably not. That rock vapor atmosphere.
Yeah, that's so
Yeah,
cool.
probably a completely molten, rocky, metallic surface.
Right.
One of the ones that has been hypothesized or suggested to be a Chthonian planet orbits its star in like 20 hours.
Right.
Tidally locked, of course.
Well, we see all these hot Jupiters. I guess you would imagine if they were there around long enough that the atmospheres would get stripped away.
That's the key thing.
Cool.
That's the key thing. It takes time.
Right.
So some of them are having, their, a mass loss rate that can be calculated, but it's like several billion years required to completely remove it, which is kind of surprising to me.
Yeah. I guess the gravity is very, on the. Well, I don't know. Yeah, I don't know.
The gravity's strong enough that it's just holding on to all those.
I can hold on to the
volatiles.
gas more easily.
It's an interesting. It's an interesting question. So part of it is how deeply does the heat penetrate?
Right.
So if it's not hot below, an optical depth of 1 or something, you're just truly just peeling it off the top.
Yeah.
Gradually, and so that would take some time.
Right.
But it would be a challenging trip to go to a Chthonian planet.
Sure.
Yes. So all sorts of exciting things are happening in the realm of space news.
Oh boy.
So much fun stuff.
First up, I would like to mention the Osiris Rex sample return because it is days away.
It is in fact 8 days, 17 hours, 51 minutes, and 19 seconds from right now.
That would be awesome if this were a live show.
I know.
Maybe you're not better than me because I would never have said that.
That's why I said from right now.
Yeah. But
that's very exciting, though.
It still will be in the future if you have downloaded the podcast on Walkabout Wednesday, because it is September 24th at 10:55 a.m. Eastern, U.S. Eastern Daylight Time in Utah, the United States. And it's kind of amazing. Once again, I'm a big fan of like Newtonian mechanics and celestial mechanics, and I'm just always find it cool how precisely we can fly stuff around the solar system.
It is stupid. It's stupid.
How cool
good
I find it, or how good we
No. I agree with you that it is remarkable how accurately we can calculate when and where those. Yeah.
Right. Yeah. So this thing, just as a reminder, Osiris Rex went to the asteroid Bennu, which is, I think, smaller than both of our asteroids.
It's pretty small.
It's less than a kilometer or so across.
This is pretty awesome because I remember at least I was out there for the launch. You were out for the launch as well, yes?
I did not go to the launch of Osiris Rex.
I was invited in.
That was the first big launch. I think I was maybe the only big space launch that I got to go see. It seems like forever ago. But now it's coming back.
It's
coming
2019?
back. So earlier than that, I believe. And so it spent some considerable amount of time at this asteroid Bennu, made a lot of really cool observations, many of which we've discussed on previous episodes. There's like this, it was spitting pebbles, this asteroid. That's one of my favorite discoveries. Mm-hmm. I'm not sure if we still really understand what's going on with that.
No.
And then it came in with an instrument called a TAG-SAM, which sort of looks like a pie pan at the end of a rod, and it sort of came down to the surface and touched the surface, and it blasted a puff of nitrogen gas to stir up the material. Of course, the gravity on this asteroid is basically zero.
Yeah.
So you kind of look at it the wrong way and particles are going to come off, right? Mm-hmm. And so it filled up the pie pan with a few pounds of asteroid stuff.
Regolith, yeah.
And sealed it up and has been flying back to Earth. Mm-hmm. And it's going to drop off the pie pan, which is going to parachute down into Utah at 10:55. On September 24th, and they're going to pick it up. And you know what's happening with the rest of the spacecraft after that?
Oh, is it gonna? It's gonna go look at Apophis.
It is.
Yeah.
Oh, that's the one that's going to kill us all, yeah?
Yeah, it's the most potentially hazardous
that we know of
asteroid that we know of, or the most potentially hazardous asteroid. It isn't definitely.
It's the potentially hazardousest.
Yes. Yes. There we go. That's it. Yeah, that's coming. I don't remember, when is it coming by Earth?
It's soonish. All the time, but it's not going to hit.
No, it's not going to hit, but it is going to get very close.
Yeah, there was one in like 2060s, I think, that people were pretty excited about. At some point, they thought, "Ooh, this one's got a non 1 in a trillion chance of." But now it's zero. Now they know it definitely isn't going to hit. Right. So it actually isn't going to kill
anybody.
Not going to kill anybody who's going to live to see it.
No.
Yeah, uncomfortably close. Apophis will be uncomfortably close in 2029.
Oh, really?
Yeah, I don't.
Oh, well, that's also when Osiris Rex, which is being renamed Osiris Apex.
Oh, I didn't know that.
Will join up with Apophis. Oh. So I imagine it's just going to fly in formation with the Earth more or less until that encounter.
That makes sense.
I don't know. It'll probably be that's 6 years from now. Geez.
Yeah, it is.
So it'll be doing some orbit matching. Between now and then. So it's being renamed Osiris Apex for Osiris Apophis Explorer. And the Osiris, if your inquiring minds want to know, stands for a bunch of like science terms like origins and spectrometry and infrared and things like that or whatever.
It's truly ridiculous.
It's a real it's a backronym.
Yeah.
So Osiris Apex means that after it drops off this material from the asteroid Bennu, it's got a new mission that really begins 6 years from now.
That's
longer
amazing.
Than the time it took to go to its original target, but it's going to spend 18 months orbiting Apophis.
So was this at all part of the plan when they first launched Osiris Rex, or was this?
I don't think so.
No, that's the kind of thing you come up with.
This is extended mission.
You always think about, what will we do maybe if everything goes well, and there might be some possibilities, but yeah. So 18 months at Apophis, which will include getting close to the surface and turning its butt towards Apophis and farting at it.
Pooping?
Yeah, no, not pooping, farting. So that there's a little blast of exhaust out of the rocket engine that cleans off the surface material so you can then turn around and look at the exposed material underneath.
Very cool.
Yeah.
Oh, that's interesting.
Yeah. So it's kind of a new mission without needing to buy a new rocket or build a new spacecraft.
Yeah.
Right.
So,
that's great.
Got to keep the thing running for another 7 or 8 years to do all that stuff.
That's great. Keep those people employed.
Keep the science coming.
Good.
Right. You had another fun spacecraft spies and asteroid story, Audrey.
Yes, I did.
You want to tell us about it? Or that wasn't meant to be the end of the conversation.
Oh, yeah. Sorry. Sure did. So Lucy, the Lucy mission.
Yeah.
I forgot that it's just a spacecraft. To me, it's like so much bigger.
Lucy is so much bigger than a spacecraft?
Yeah, it's the community. It's the targets. It's the people.
It's your Cassini.
It's my Cassini. Lucy is going to fly by its first target in like a month, like a little over a month.
Is this a planned target or an accidentally we discovered that, oh, by the way, we're going by this thing target?
Well, it wasn't accidentally discovered. It was very intentionally discovered, but it was after launch. Yeah, there were a couple of people on the team that were like, are we going to go by any other main belt asteroids at any point? And so one person on the team really went into it and found this asteroid that has since been named Dinky.
Dinky.
Yeah, it's the Ethiopian name for the Lucy fossil.
Oh,
yeah.
I like it.
And I think it's like loosely translated to something like you are marvelous, something. So it's like, it's a very nice name. But the navigation cameras on the Lucy spacecraft have found Dinky, is what we're calling it sometimes. Okay. Which that might be like insulting. I don't know.
Is it? Dinky? How does it compare in size to my asteroid? This is all that I care about.
So it's a different. I think it's an S type. It's smaller. It's much smaller. It's about 1 kilometer. It's like half the size.
Dinky.
Yeah, it's dinky.
So it's accidentally flying by it. It wasn't accidentally discovered that we're flying by it, but we're accidentally flying by it.
Yeah. So it's going to be really exciting, and so we found it. The navigation cameras. This is all like a test of like the instrumentation.
Right,
this is any science that comes out of it is bonus, and obviously all of us scientists want to get all the science that can be gotten out of it.
That's one of the things that kind of bothers me about scientists, actually. They're like, science.
What?
I don't know. Sometimes I get like...
You're just like,
it's like, calm down already.
Engineer something.
No,
let's talk about Blackpink.
Exactly. There's more to life than like asteroid spectra. That's all I'm saying.
Yeah, but... we don't have that many like spectra,
except for asteroid scientists, apparently.
Yeah, apparently.
Listen, this is very
but
exciting.
It's a great opportunity to do trial runs for the spacecraft's
it's a trial run.
operations.
Yeah. So first part of that is we found it.
Yes.
Huzzah!
Camera works. You'll collect some data. You'll also practice sort of your analysis techniques and things like that.
Exactly.
Your software that you've got for doing things.
Yeah.
And then remind us when Lucy gets to its first actual non-accidental target out in the vicinity of Jupiter.
First Trojan target. I should know that off the top of my head, but I'm just gonna vamp do.
Okay. while you're
August 27th, 2027.
Okay.
A little while yet.
So, and there is another intentional flyby before it gets to that one of Don Johnson or something.
Donald Johansson, very close.
And that one is happening.
That one will be April 20th, 2025.
Okay.
Yeah.
So the pace is starting to pick up for you guys on the Lucy team.
Yeah, it's really exciting.
Yeah.
Oh, thank you.
Yeah. Other space news, there's an annular eclipse coming up on October 14th.
Ooh.
That is cutting across North America. So this one goes from the northwest of the United States on a southeasterly path, I believe. But those of our listeners in the Americas can check out greatamericaneclipse.com for all sorts of wonderful details to see that. An annular eclipse is one in which the moon passes directly in front of the sun, but because
but the moon is a little further away than it usually is. I mean, the moon is on an elliptical path, which means its angular size in the sky is just a little bit smaller than the sun's angular size, which means that even when it's in totality, it's not totally covering the sun, so you can't look right at it.
So you don't get all of those like cool fringy
you can't see the corona and all the cool stuff you can see during a total solar eclipse.
Even the tiniest rim of the solar photosphere is so freaking bright.
Yeah, just 1% or 0.5% of the it's just way too bright. Yeah, it washes everything else out. Wow. So,
but it produces a sort of interesting. You have to obviously you have to use protection.
So if you have your eclipse glasses and look at it, I think it's pretty awesome because it's just and you see this really cool ring of light around the outside of pretty cool. But very different from the normal total solar eclipse.
Right, not to be looked at without appropriate protection.
So there's also going to be a total solar eclipse in 2024 in April
8th, yes.
And it looks like
they cross in San Antonio.
Yeah, like that's so cool. So if you're in San Antonio...
Is that right? San
do you
Antonio,
have a spare room?
Yeah. Gets them both. And that one goes also across North America from the southwest to the northeast. And that one I'm going to try to catch totality.
Yeah. Everyone should, if they can. I mean, obviously, not everyone can, but it's a once in a lifetime. I mean, I say twice in a lifetime now because we had the 2016 or whatever that one, the last 2017 one was phenomenal. But see it.
Let's see. Other observational news, JWST corner.
Yeah, the observatory.
Okay. That's our dome is broken. We got to work on our observatory dome opening sound effects.
It's a great one.
Yeah.
So there's actually been a lot of JWST like news and stuff that came out But the one that I saw that I really liked is of Saturn.
Yeah, one of my favorite planets.
Yeah, and so it's a team from the UK that has been really nice to me because they're also using MIRI data. So they have MIRI data of the rings and of Saturn.
What's MIRI?
The mid-infrared instrument on JWST.
Okay.
That's your favorite instrument, right?
It's my favorite and least favorite.
Because it's got some issues.
But these data are incredible. And from reading this article, it seems like it's the first time that we have observed in these wavelength regions autumn on Saturn. Which I don't fully understand why that is novel, because I thought, there was a whole spacecraft and stuff that went around Saturn.
There was a whole spacecraft and stuff
that went around
Saturn. It was called Cassini.
Oh!
And it orbited Saturn for almost a half a Saturn year.
Oh, duh. Okay, so now it's getting into autumn. And now...
Well, we saw autumn, but in one hemisphere, right? So we saw from close to the southern summer solstice to the northern summer solstice, but not back again.
Right.
So we saw we saw southern summer, and southern winter. No, we saw southern. We saw southern summer to northern summer. That's half a year. We saw half a year.
Great. And now we're seeing more.
Yeah.
So southern summer to southern winter would give you southern spring, but no, that's southern fall. Anyway, I don't know.
We saw it going up, but not coming back down. So it kind of, we didn't see exactly a full half of a year. But also we're looking, it's different kinds of instruments. JWST in which camera you were talking about?
MIRI. Yeah.
And what is it about? What's MIRI's wavelength range?
The mid-infrared, so it's from like 5-ish to like 40-ish microns.
Okay. So Cassini had a visual and infrared mapping spectrograph or spectrometer that went out to 5.2 microns.
Oh, okay.
And then it had an infrared, like a far infrared, thermal infrared, which maybe did not cover that wavelength range.
Or maybe
Sears.
Yeah.
Yeah. But what did it see? What did it see that's cool and amazing?
They made a movie about it, and
colors
it looked cool.
And the trees.
There were colors. Yeah, that was
colors.
The exciting.
The trees were.
It was really
changing.
Pretty.
That's what I want to see.
Leaves were falling.
That's what I like about autumn.
Right. Autumn in which hemisphere, Audrey?
Northern
autumn.
Yeah.
Okay.
At least that's where the picture is.
That sounds right, because in 2017 or so, it was northern summer solstice around that time.
Perfect.
At the end of the mission.
Yeah.
Well, it's cool. Saturn is a cool looking beast. The only other space news that I have is this report that's been in the news that the SLS is unaffordable.
Oh, no.
What?
This is NASA's space launch system that is the centerpiece of the Artemis program to take astronauts back to the moon.
That's kind of a big deal.
It's kind of a big deal.
What does that mean, unaffordable?
Well, that's the excellent and key question. Unaffordable, I guess, means that somebody has deemed that it's more expensive than what the people who pay for it are willing to pay.
What it sounds like to me is that someone deemed that it's not worth it. Like, the price is the price. And
the price is the price. And in the grand scheme of things, in terms of the amount of money that the United States spends on stuff, it is affordable.
Yeah.
Right.
Yeah, exactly.
Even if it's sort of like twice or 5 times as much as you thought it was going to be.
What are we talking about here? What are we talking cash-wise?
Well,
more or less than my checking account.
It's billions, right? It's
about
billions,
the amount of your checking account.
It's maybe like $1 billion per launch or something like that. It's in that ballpark.
How can that be unaffordable when there are individual citizens in this country that have 100 times that much money.
That's what I'm saying.
That's the whole thing is like there have been all these headlines that it was deemed unaffordable, but it's just a matter of will, I guess.
Oh, the deeming is the key word. Deemed.
Yeah. It's certainly like there are certain things you can't do because like it won't work, right?
Yeah.
This is not one of those things.
Yeah. So what's going to happen?
That is unclear because the next mission of the Artemis program, as you know, the Artemis 2, which is, going to happen, astronauts are just going to go for a sort of a joyride around the moon, test out all the systems, make sure things work, but they're not landing. To land on the moon, they've subcontracted to SpaceX, and that is its whole other issue where there are still technical issues that haven't been demonstrated yet. So their super heavy Starship has to be proven to work
and not blow up.
And take the Starship. I get the names wrong, but it carries a sort of shiny Flash Gordon rocket on the top of this ginormous booster, and that Flash Gordon rocket's the one that's going to dock with a NASA rocket in lunar orbit and take the astronauts down to the surface and blast back off. And NASA's requiring, quite reasonably, I would say, SpaceX to demonstrate that they can fly this thing to the moon, land it on the moon, and take back off from the moon before they put people on it.
That sounds very reasonable
This
to
thing
me.
hasn't even actually flown yet.
Right.
Well, it flew up a bit and blew up, as you said.
And then exploded.
But they're getting close to their next launch. So, with all of that exciting space news behind us, let us get our trivia and then transition to the death of the standard cosmological model, thanks to Jim Cooney.
Thanks, Jim.
Sorry, everybody.
You remember that our sponsor today was
Chthonian planets.
Chthonian planets, hypothesized gas giant planets who have migrated inward so close to their stars that their atmospheres have been boiled away, relieving the core of a giant planet, which I just think is a cool thing to think about.
Yeah.
Our trivia, although remember that the core of a giant planet presumably has lots of ice in it.
Right.
That's why it got to be a giant planet in the first place.
Right.
So I wonder what,
Well, that would get volatilized off too, wouldn't it?
So then you've got
Then
this
you're just
mix
left
of
with the rock and metal.
rock and ice and metal. So it's an interesting evolution for these.
Yeah, I was thinking when you just said that, I was like, well, maybe instead of having their atmospheres boiled off, they just never got them in the first place. Like if you took the thing that made Jupiter, you made this big core that was like 10 times the mass of Earth or something like that, and then started collecting a bunch of hydrogen and helium from the.
Right.
What if that thing like spiraled in before it was able to collect all that hydrogen and helium?
Sure.
Then that would still be a Chthonian planet. Yeah.
Yes.
Weird.
Yeah.
Anyway.
Giant planet core, naked giant planet core. It's like a naked mole rat. Our trivia today is about high planetary temperatures.
Okay.
What is the hottest temperature recorded on Earth when what planet has the highest average temperature, and what is it? And then there are some additional follow-ons.
Okay.
All right.
The average surface temperature of the three innermost terrestrial planets.
I don't remember specific numbers.
Well, that's trivia. That's what makes it trivial.
Oh,
I'm going to dominate this one
You're welcome.
thank you.
Okay.
because I know inner planets.
Oh, really?
Do you really?
No.
Not
we'll
at
see.
all.
No, we'll see. No,
I like the confidence.
I'm going to dominate it anyway. I got
Right.
it. I got
Tell
you.
us about Gordo or whoever he is.
El Gordo.
The Gord?
El Gordo.
Does that mean the Gord?
No, it means the fat one.
Oh, really?
The fat one. Yeah. So El Gordo is a galaxy cluster, or a cluster of galaxies that is, as the name suggests, huge.
Okay, but it's not a supercluster, or is it? It's a.
No, it's
Is it
a
like
cluster.
the local group? So we're talking dozens of galaxies?
No,
or thousands of galaxies?
It's thousands of galaxies. It actually is the most massive galaxy cluster yet seen.
Okay.
Has a mass of something like 1,000 trillion solar masses.
1,000 trillion solar masses. And for context, the Milky Way is about 500 billion solar masses.
Yeah.
Right?
trillion. Something like that.
About a trillion?
About a trillion. It's got a lot of gas, mass and gas. Okay. So
about 1,000 times the mass of the Milky Way. And are these galaxies gravitationally bound to each other?
Yes. Yeah, that's what makes a thing a cluster is gravity. Superclusters are generally not gravitationally bound. A cluster is.
Okay.
So this is a huge thing, but the cool parts about it, I mean, there's a bunch of cool things about it because it's got a lot of superlatives associated with it. It's the biggest.
Is it bigger than my asteroid?
It is moderately bigger than your asteroid. It's amazing that in one podcast we talk about things that are 2 dinky kilometers and
hey,
yeah.
Dinky was only 1 kilometer. I'll have you know.
All right. So this thing is huge. The one really cool thing about it is it's kind of almost not one cluster. It's 2 colliding clusters, actually. So it's two galaxy clusters that are in the process of colliding with one another. So there's kind of 2 distinct populations of these things moving at each other. And
we know this from Doppler shift of the galaxies.
Right.
Okay.
And it's a challenge, actually, to explain this thing because...
The fact that they're moving towards each other?
No, the fact that it's very large and they're moving toward each other quite quickly at millions of miles an hour at a very early time in the universe. So this is also a very distant object. So it's at a redshift of 0.87. It's basically like we're seeing it as it was when the universe was about half the current age that it is.
Okay.
So it's, 7 billion-ish light years away or something like this. This is basically at that point in the universe's evolution, there shouldn't have been clusters that large moving that fast towards each other.
Based on our standard
standard cosmological story, which we call the lambda CDM cosmology, right? The
CDM for cold dark matter,
right? Lambda for
Lambs.
cosmological constant. But that our standard picture of things, structure largely goes kind of bottom up. That is, it starts off small with like clusters of stars that glob together that make galaxies, which glob together to make clusters, and so forth, and which means that the bigger structures in the universe shouldn't have formed till later in the universe.
Okay, so on the chicken and egg analogy, the stars come before the galaxies. In other words, you do not form the first stars in the universe from a trillion solar mass cloud of gas.
Right.
You form it from a one solar mass cloud of gas a trillion times.
Right.
And then those guys get together.
Right. Right. So that's the standard picture, and in that picture, this is very similar to something we've discussed in recent episodes where JWST is seeing larger, more mature galaxies at that very edge, in the very early universe than we would have thought. It's the same kind of thing.
General problem. Things that are happening earlier than we think they should have.
Right.
Is it a problem if it keeps coming up? Like, it sounds like, okay, we have the standard idea, but if we're consistently seeing things happening earlier on, it sounds like a good thing. Okay, maybe we have to, rewrite some equations and stuff, but,
Is that all?
Okay, good. We're seeing stuff forming earlier on using this method. We're seeing stuff forming earlier on using this one, and this one, and this one, and this one. So it sounds like it's not a problem. It sounds like it's
a problem because the theory predicts that should not happen. And so what that means, when we say problem, it's just
the theorists.
Attention. Right. The theorists say this shouldn't happen.
Like I said, just rewrite the
observational astronomers say, look, it's happened. And then the theorists have to say, nah, you're wrong, or something like that. So, I mean,
it is a problem to be solved.
Right.
It is a question.
It is a question. So
why does this thing look the way that it does?
Right.
And that's what...
And how serious a problem this is depends on who you ask. There are a significant and growing-ish number of scientists who say this is a fairly serious problem that we
JWST is the Tower of Pisa is leaning.
Yeah. I think for a lot of people, this El Gordo thing is a more serious problem than the early galaxies.
Stuff.
I think we've kind of been able to wiggle out of by adjusting a few numbers here and there, wiggle our way out of the JWST problems.
What if we change this 2 to a 3?
Yeah. But El Gordo, basically what they did was some groups, you can run simulations based on the theory, right? You run these computer simulations to say, this is how structure should go. And the big picture looks just like our universe, which is like a great success of the theory. But you shouldn't see these big giant structures colliding in the early universe. And when you run the simulations, you can run them over and over and over again. You just don't see structures like that. And you can calculate kind of what the odds of seeing one. I mean, they'll happen. I mean, any statistical fluky thing will happen. But the odds of seeing it in our universe are something like 1 in 10 to the minus 10 or something like that in the volume that we've looked in. And that's equivalent to something like 6 sigma kind of a thing, like where it's not very satisfying. So to be clear, I think still the majority of cosmologists say this isn't a catastrophic problem. This is
to throw out the Lambda
no.
model.
It's just there's some details that we need to iron out here.
Right. So these simulations are complicated because you can't actually simulate exactly the universe, because the universe has got much more stuff going on and much more time than your computers can handle.
Right.
So they always involve approximations and
they do
simplifications that treat some big complicated thing in some simplified way, and then they put that all together.
Yeah. So it is possible that the issue is in the simulations. It's possible that the issue is in the observations. It's possible that the issue is in the theory. Honestly, I think it's going to be something like like we have this in cosmology. We have this idea of what the early ripples in the universe look like. The early ripples are what the structure grows from, those seeds, and so we make some very simple assumptions about what they look like, but they actually look a little bit different than that because of these little initial fluctuations are born of quantum things, really. In the very early universe, the pre-inflationary universe, you have little quantum fluctuations that when the universe inflates, those quantum fluctuations grow to big-size things. But quantum fluctuations can work weirdly, and so you can basically have these like weird tails on like a Gaussian distribution that don't look Gaussian or something like that. And that's what something like a weird one-off in the universe that you find is something that you might see in a tail of a distribution, right? And if the tails are different than you're describing in your simulation, then you're going to occasionally get weird things. And so I think it's just a devil in details thing and not a really big thing. But it is at least interesting. It's interesting to see challenges to the standard picture, and you can't just throw them out. You have to.
Yeah. And so, I mean, one of the fascinating things about what you were just saying is that stuff going back, that the largest, we were talking about this in the last episode, the Ho'olelana bubble, and now another very, very large cosmological structure. I guess this isn't really a cosmological structure since it's a gravitationally bound
it's
cluster, but in any event, it's a gigantic cluster of galaxies whose existence can maybe traces back to the details of quantum scale.
I know,
which means tiny unimaginably small scale stuff in the unimaginably early stages of the universe. So that connection between
that's really awesome.
The Big Bang era and today is kind of amazing.
It really is.
Yeah.
Beautiful.
All right. Hot planets. What's the highest temperature ever measured on Earth? I said the hosts are hot.
Sure did.
98.6-ish, but what do you think for
hottest temperature recorded on Earth?
Like natural or
the hottest temperature? Not like in your oven.
Yeah, well,
that's a good question, though. Yeah, and I wonder.
Thinking
that's also an interesting trivia thing, like in physics labs or something like that.
Yeah.
Anyway,
no,
that's not the question.
At a weather station.
200 Fahrenheit.
I think it's something like 135.
Jim is going to get this one, Audrey.
I'm not saying it's like in an area that's like
So 134 is the highest recorded temperature. 134 Fahrenheit, 56.7 Celsius.
Is that in Death Valley?
In Death Valley.
I was going to guess Death Valley.
Have a guess when?
Not that long ago.
Last week.
Yeah. Actually, 1913. Believe it or not, and some people are in the not category.
Yeah, I think there's a lot of people that doubt
that measurement, thermometers back then, they installed that weather station in Death Valley in 1911. There, of course, may have been other high temperatures like that in other places where nobody bothered to install a weather station. With really unquestioned, accurate, modern instruments, still in Death Valley, 130 has been measured a couple of times very recently, 2020 and 2021. The hottest years on record for planet Earth here tie between what 2 years?
2023 and 2022.
It's a very good guess.
Yeah, I thought this
We're
year...
not done with 2023, so
2022 and 2021.
Okay.
Yeah, I'm with that.
2016 and 2020, because we're on this general upward trend, but there are these global oscillations due to El Nino.
Right.
2023 is poised to set a new record. It looks like it's on track to do that. Which planet has the highest average temperature?
Ugh.
Venus.
Yeah, Venus.
Correct, at about 867 Fahrenheit. That's because it's got this massive atmosphere that makes it the same temperature all the way around, doesn't let heat get out. What is Mercury's average surface temperature, which is closer, significantly closer to the sun than Venus, but it doesn't have an atmosphere, can act as a blanket, and therefore the night side gets quite cold.
Yeah, I thought the day side was on the order of 800 Fahrenheit, and the night side was on the order of minus 270 or something.
Jim said he was making jokes, but he is nailing the interplanet stuff.
My God. Yeah, I agree. Whatever Jim said.
Peak surface temperature on the day side Mercury is 800 Fahrenheit. Night side temperature is below 200 below zero.
Why do you know this?
Colder
You
than 200 below
Googled.
zero.
I know. I teach
You
this.
cheated.
I teach this.
Yeah. So there's more than 1,000 degrees Fahrenheit difference between the day side and the night side of Mercury. How about Earth? What's the average global surface temperature?
Oh.
I want to say like 50 Fahrenheit.
Yep, me too. Okay, fine.
You gotta go either 51 or 49.
All
Come
right.
on.
My brain went to like 275 Kelvin, which is
That's cold.
yeah.
No, what is
No, that's like 70. But I don't think that I'm just gonna say 70 and be wrong.
No, that's not 70, that's 35
35.
Kelvin.
Right.
275 is 2 Celsius, which is just above freezing. So
But I'm going to say 75 degrees is the average Earth temperature.
75 Fahrenheit.
That's right.
Jim's going to get it.
No.
59 Fahrenheit.
Who would
If
have
you'd just gone for
thought?
51, you'd have had it.
I would have had it, but it
Right.
wouldn't have been. It wouldn't have been a satisfying win.
While it may have felt like taking a walk through Death Valley, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts. You can ask us questions via the ancient technology of email at wtg@ucf.edu. Our theme music was composed by Richard Rusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in all the hot places. Stay safe. I'm Josh Caldwell.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the Astrocork, signing off until the next episode of Walkabout the Galaxy.
El Gordo.
Gordo.
Chthonic.